Welcome back to our session. The I was still trying to establish to us the how we determine the power that is measured by a wattmeter. That the power that is measured by the wattmeter is made up of the current reading and the voltage reading combined with the power factor, which is represented by this. That is where V is the voltage reading, the reading in the voltage coil, and I is the reading in the current coil. Then multiplied by the power factor, and the power factor, which is cos phi, where phi is the angle between the voltage and the current. That is the angle between the voltage and the current, or we call it even the load angle. The load angle, or even the power factor angle. That is phi, which is the voltage angle minus the current angle. The voltage angle, that is the angle of the voltage minus the current angle, the angle of the current minus the current angle. That is the phi. Now, let's talk about the methods of measuring power in three-phase circuits. There are three methods that are used in measuring the power, measuring three-phase power in three-phase circuits. There are three main methods. We have what we call the single wattmeter method, for measuring three-phase power in three-phase circuits. Number one, we have the single wattmeter method. Single wattmeter method, where we only use 1 wattmeter across a line. Then we have the 2 wattmeter method. Then number 3, we have the 3 wattmeter method. Those are the 3 methods that they use in measuring power in a three-phase power system. Now, the single wattmeter method, which is 1 wattmeter method. The 1 wattmeter method, which we also call the single wattmeter method. The 1 wattmeter method, you can use it to measure power of any balanced three-phase system. That is, any balanced three-phase system. You can use the single wattmeter method without breaking the phase. That is, 1 wattmeter method can be used to measure power in any balanced three-phase system. As long as it is balanced, you can use single wattmeter method to measure the power in those 3 phases without needing to break the phase. especially on star connected system. On star connected system, in balanced three-phase system, without breaking the phase. So let's look at a star connected system. In this case that I told you, you can use Wattmeter method. You can use one Wattmeter method on balanced three-phase system, whether it is star we represent it like this, or delta system. As long as it is balanced, we can use single Wattmeter method to carry out the measurement. Now, let's look at, for example, a single Wattmeter method for measuring power in a star connected system, three-phase balanced system. This is line A, C, and B. This is going to the load. This is representing the load. This is coming from the supply. From the supply to the load. Then we have the wattmeter placed on line A, and we have the neutral wire to balance the system. We connect the voltage leg of the wattmeter. We connect it to the neutral wire, while the current coil is connected to line A. So, looking at this particular figure, if you want to use the wattmeter, this is one wattmeter only to use. You want to use it to determine the total power in this load. Now, what you do is this. Because it is a balanced system, once you measure the power in this line, that is the power that you measure in this phase, this is phase VAL. The power that you measure in this, all you need to do is you multiply it by 3. That will give you the total power measured in the load. That is with the star connected system. The wattmeter measure the phase power that is then multiplied by 3 to find the total power in a balanced load. That is for delta connected system. Let us look at, for star connected system, Let us look at delta connected system. This is a delta connected system this is line A, C, B. And let us put our wattmeter first in line A. When we put it, the voltage leg, this is a little bit different from the connection that you had in that star connected system. The voltage leg of the wattmeter is connected straight to any line. We can connect it to any other line that is free, and you determine the wattmeter reading at that time. Then the second time you disconnect that voltage coil from this and connect it also to another line B also, and you determine the wattmeter reading also in that instance. So that means the two wattmeter reading that you measured when the voltage coil is connected to C, and you take the voltage coil away and you connect it to B, and you measure the wattmeter reading again. The two wattmeter readings that you take, you add it together, that will give you the total wattmeter reading, the total load consumed power by this load, the total reading of the wattmeter on this particular circuit. That is, the voltage coil is connected alternately between the lines and the other two lines. The total power is then determined from the two readings on the wattmeter. And that is how to determine, using single wattmeter method, to measure power in a delta connected system. Now, when we look, let us talk briefly about the phasor diagram. When you look at this, IA is the current that flows through this line, while IC flows through, while IB is supposed to flow through this line. Right. Now, the current IA in this instance is flowing through the wattmeter, and the phase difference, the current, these are the lines into the load, but these are the phases of the load. So this is a phase AB, while this is A, this is B, and this is C. These nodes, these are A node, B node, and C node. So the current IAB is flowing from A to B, and current IBC is flowing from B to C, and this one is reversing, is flowing back from from C to A. That is current ICA. So if you look at it very well, you will see that IA, which is this current, is a phasor difference of IAB and ICA. That is when you consider this node. So when you use Kirchhoff's current law to determine the summation of the current at that node, taking node A, if IA, every current flowing in is assumed to be positive and the one flowing away to be negative by Kirchhoff's current law, IA can be taken as positive, while IAB is flowing away from the node as taken as minus IAB, then ICA is flowing into the node, which is plus ICA. The total summation, according to Kirchhoff's law, is equal to 0. When it says all the current, the summation of the current flowing away and into a node is equal to 0, the summation. So if IA is minus IAB plus ICA is equal to 0, then IA will be what? It will be IAB minus ICA. So that means our IA that is flowing through the coil of the wattmeter is the phasor difference of IAB and the ICA. So it's a phasor sum of IAB and ICA reverse based on these negatives. So IA is the phasor sum of IAB and ICA reversed. So when you look at, let us take, for example, this phasor diagram that represents a negative phase sequence. I'm going to talk about the sequences later in the course of our studies. Let's say we have our BA. This is our, okay. Let's say we have our VAB. This is our VAB, and this is our VBC, and this is our VCA, which represents a negative phase sequence. Don't worry, if you don't understand, you can let me know later through the WhatsApp, and I will see how to throw more light into this for you. So this is VAB, VBC, and VCA. And going by the fact that we say we are dealing with inductive